All right, in this section, we're going to do something very similar. So we're going to do more work with confidence intervals and also with means. So this is going to be, I think, a nice review anyway of that whole process. But in this case, we have something that's different. And this time, the sigma, remember, which is the population standard deviation, is unknown. And I feel like this is probably what occurs most often in the real world, right? If you're searching or if you're doing research on a new subject, then likely you wouldn't have data already from someone else's research where the sigma is known, right? You could, right? So if you're updating research or if things have changed over the years, but a lot of times if you are sampling, you don't know the population information at all. So this is probably what's going to occur more often than not. So you know nothing about the population and you really only have your sample data to work with. Now, when that happens, when sigma is unknown, we do not use the normal, which is the z distribution, for our critical values, okay? We use a new distribution called the t distribution, or sometimes called the student t distribution if you've heard it before. So this is the change we're going to make. So everything's going to be very similar, but those critical values that we found last class, those z values, we can't use here. We're going to use t values instead. So we're going to have to find different critical values. But otherwise, the processes are very similar. So in many real-life situations, the population standard deviation, as I mentioned, is unknown. So how can you construct a confidence interval for a population mean when sigma is not known? So again, we still have a simple random sample that is drawn from a population that is normal or has a sample size of 30 or more. What we can do is use the sample standard deviation to estimate the population standard deviation instead. But again, it's not normal, so we're going to use what's called the t distribution instead. So if the distribution of a random variable x is approximately normal, then t is given by this value here, and it follows a t distribution. Critical values of t are denoted as tc, so instead of using z, use t. So some things to note here about the t distribution, it actually looks pretty similar to the normal curve, but it's a little bit different. So the mean, median, and mode are all still equal to 0. It is bell-shaped and symmetric about the mean. And the total area under the distribution is still equal to 1. So you have very similar things to start with, right? It does change though. So the tail in the t distribution are a bit thicker than those in the standard deviation. In the standard normal distribution. But again, so here they have the standard normal curve in blue, whereas your t curve, two examples are one's in black and one is in like a beige color. So they're a little bit thicker there. They do eventually get close to the x-axis, but it just takes a little bit longer. Here's a big change. The standard deviation for the t distribution varies with sample size, but is greater than 1. So in the normal curve, that standard normal curve, the standard deviation is always 1. In the t, it's not. It does change. The t distribution is a family of curves. So again, they all kind of look similar, but they're a family, so they're not all the exact same curve all the time. Each determined by a parameter called the degrees of freedom. And the degrees of freedom, which is abbreviated DF, are the number of free choices left after a sample statistic, such as the sample mean, is calculated. So what you really need to know there is that the degrees of freedom is just equal to the sample size minus 1. Okay, so again, n is still your sample size. So sample size minus 1. As the degrees of freedom increase, so as your sample size gets larger, the t distribution does approach the standard normal distribution, okay? So as your sample size gets larger there, the t distribution looks much more like that regular normal distribution that we're used to. They have a lot of similarities anyway, so it just becomes more and more looking like that normal curve. So the big change here, again, because the basic formula is going to be the same, is that how do we find these critical t values? And there's two ways to do it, just like there was in the last section for the z values. You can either use the table in the back of the book, or you can use technology. So I'll show you both here. I still do recommend drawing a picture to start though, so that you can, again, see the area that you're looking for. So it's just very similar to what we've already done. It's just that you're using t values and not z values. So let's find the critical value for a 95% confidence level with a sample size of 15. Now, with t values, it is tricky because they're based on sample size as well. So with z values, I was able to give you like a couple standard ones that we use a lot. With t values, I can't do that because they change depending on the sample size. So you're probably going to have to find the t value for every example that you go ahead and do on the. So this is a piece from the back of the book. So this is table 5 in Appendix B. And our sample size is 15 here. So n is 15, which means the degrees of freedom is n minus 1, which is 14. So when you're using the table, one thing you have to look at would be the degrees of freedom. The other thing you're going to look at is the level of confidence. Okay, so there are other ways to think of this table using tails as well, but I think for you guys, probably the easiest thing to think of is just that level of confidence. So use that top number there, and then you're going to go ahead and match them up, and that's going to give you your critical t value. And just like before, it is symmetric. So as long as you get the one on the right, then the one on the left is going to be already given for you. So you don't need to find both of them separately. You can just find one. Now, the table here is actually pretty easy to use. It's a little bit different than the standard normal table where everything is always area to the left. You don't have to worry about that with the table here. So let me go back and just show you that table, the larger version of the table. Sorry, guys, let me just find it already. Okay. All right. So here is that table in the back of your book. And you can see it has degrees of freedom here, and it actually goes down till 40 straight, and then it jumps to 45, 50, 60, 70, 80, 90, 100, 500, 1,000. So it's not every single value, but it does have a lot of them here. And the nice thing is, if you use the level of confidence feature, you don't have to worry about area to the left. You can just find that percent that you want and scroll down. So here our degrees of freedom was 14, and our level of confidence was 95. So we were able to get that critical value very quickly. So again, the positive of the t-table is that you don't have to think about area to the left at all. You can just use that confidence level that you want and scroll on down and get your answer, which is really nice. So our critical t-value here was that 2.145. So this is probably one of those rare cases where I would probably recommend the table just because it's going to actually be faster. If you want to use technology, though, it's very similar to inverse norm that we did before. So you want to remember, though, when you're using technology, so instead of using inverse norm, you're going to press second bars, and you're going to use inverse t because we're doing the t distribution. And again, you do have to put an area to the left when you use the calculator and your degrees of freedom. That's what you have to enter. So if I'm looking for this value right here, and I want the area to the left, well, I have 95% plus another 2.5%, right? So if I'm looking for a 95% confidence, again, that's the part in the middle. So the middle is 95%. That means I have 5% left over, and that 5% has to get split on each side. So you have 2.5% on the right tail, and you have 2.5% on the left tail. So the area to the left of this critical value is 95 plus 2.5. So our area in this case is going to be 97.5%, which ends up being 0.975. Okay, so I'm going to press second and then bars. And you're going to see inverse t, which is just like inverse norm, but again, with the t distribution. My area to the left is 0.975, and my degrees of freedom is 14. So when I do that, I get 2.1447, which does round to 2.145. So that's how we're going to find our critical t values here. If you want to use a calculator, then again, just keep in mind, whenever you do these inverse calculations, whether it's the norm or the t, it's always area to the left. For the t table, it's very easy though, because you don't have to worry about area to the left. You can just use the number up top, okay? If you want to use area to the left, then you can see in one tail, you would have that 2.5%. And if you combine the two tails together, you have the 5% left over. So that's kind of what those other values briefly mean. Okay. One quick note here, if you're using the table and the number of degrees of freedom you need is not in the table, use the closest number in the table that is less than the value you need, or use technology. So again, that table doesn't contain every single value. So to err on the side of caution, use the closest number that is less than it. This is the conservative approach. It will yield a larger confidence interval with a slightly higher level of confidence. So your interval will be slightly wider, but it's better to be more confident than less confident in this case.